Imagine trying to carve a really complex shape into, like, paper-thin hardened steel, but you're using a traditional physical blade.
Yeah, that mechanical stress is going to warp the metal long before you even finish the cut.
Right, which is just a total nightmare scenario when you're engineering high-cycle precision components. You need, well, absolute geometric perfection.
Exactly. But the very act of forcing a tool through the metal just ruins its structural integrity from the start.
So today we're doing a deep dive into a stack of engineering notes to see how modern R&D solves this. And spoiler, they abandon brute force entirely.
Which is fascinating. We're looking at advanced techniques that shape metal without applying a single ounce of physical pressure.
Yeah, relying instead on electricity, chemistry, and light. And we're going to unpack how these methods actually dictate the physical performance of the mechanical systems you rely on.
Because, when you're building the machinery of the future, traditional saws and drills just introduce residual stresses.
It practically guarantees premature failure, right? So the first workaround the notes highlight is wider electrical discharge machining, or WEDM.
Right, WEDM. Instead of a blade, it uses a continuously moving fine wire that never actually touches the metal.
Which is wild. It just uses electrical sparks to literally melt and vaporize the material right in front of it. Zero cutting force.
And that lack of physical force is exactly why the notes specify using it to cut the thin-walled profile of a flex spline.
Oh, because the metal is incredibly delicate.
Exactly. A physical blade would just bend the walls during the cut, but the wire glides through without disturbing the surrounding atomic structure.
It makes me think of using a heated wire to effortlessly slice through a block of styrofoam, but applied to solid steel.
That is a great analogy.
But a wire still acts like a bandsaw, right? It has to cut straight through the material. What if engineers need to carve out a blind cavity or a complex internal pocket?
Well, then you need a different approach.
I mean, why not just use a really tough diamond tip drill for those internal cuts?
Because a drill, no matter how tough it is, still relies on mechanical force and friction. And more importantly, drills can really only make round holes.
Good point. So what do they use when they need complex cavities in hardened steel carriers?
They switch to sinker EDM. So instead of a wire, you machine a custom-shaped electrode, maybe a star shape or a specific gear profile.
And you literally sink that electrode into the metal.
Right. And the sparks erode the exact negative space of your shape right into the steel.
That elegantly solves the physical force issue. But you're still relying on sparks.
Yeah, and sparks mean intense, localized heat.
Right, so if you're building a highly flexible component that has to bend millions of times, wouldn't that thermal shock create micro cracks? Or warp the metal, much like a physical blade would?
It absolutely would. Thermal impact severely compromises fatigue life.
So what's the solution there?
When engineers need to avoid heat entirely, they switch to electrochemical machining, or ECM. This is where we start melting metal and start removing it at the atomic level.
Oh, through anodic dissolution. Wait, so if you're running a current through an electrolyte solution between the tool and the part,
the metal atoms are actually losing their electrons.
And dissolving directly into the fluid.
Yeah.
You are stripping the surface away atom by atom. It's essentially reverse electroplating.
That is the exact mechanism, and the physical impact of removing material that way is just profound.
Because you aren't tearing or melting the metal at all.
Right. ECM leaves a completely stress-free surface finish. For high-cycle components, this drastically improves their lifespan.
Because there are zero microscopic stress risers or heat-affected zones to cause a failure down the line.
Precisely. But even pulling atoms away one by one electrically isn't always the right tool.
Yeah, the notes mention that when engineers need to mass-produce ultra-thin parts, like spring plates, with micron-level precision, they actually switch from electrical methods to chemistry.
Right, with photochemical etching,
Right.
PCE, it bypasses traditional machining entirely.
So you print a photoresist mask directly onto the metal sheet, covering exactly the shape you want to keep.
And then you submerge it in a chemical bath. The exposed metal safely dissolves away.
It's a completely cold, frictionless process.
Totally cold.
So we have these incredible ways to shape the metal perfectly, without force or heat. But once the part is finished and installed in a system, it still has to physically interact with other moving parts.
Yeah, friction is still a reality.
Which brings us to the final frontier in these notes surface modification.
Right. Once the macroscopic shape is cut, engineers use laser micromachining.
And they aren't using high-energy lasers to cut the part, are they?
No, they're using them to fundamentally alter the surface microstructures.
The specific application and the sources for this just blew my mind. Engineers use these lasers to ablate tiny, localized oil reservoirs directly onto the surface of gear teeth.
It's brilliant. They are digging microscopic swimming pools for the lubricating oil right where the gears mesh.
It completely reframes how we think about manufacturing.
It really does. It's no longer just about cutting a shape to tight tolerances. It's about engineering exactly how that surface will behave and interact in the physical world.
Precision transmission engineering has clearly evolved past brute force. We are shaping the future of machinery with atomic precision.
Relying on electricity, chemistry, and light to solve complex physical problems.
Which leaves you with this to think about. As these zero-stress, atomic-level manufacturing techniques become more refined, how will the ability to engineer friction-defying microscopic mechanical parts change the limits of the everyday machines you rely on?